It's the most powerful technology of our time. But how does artificial intelligence actually work? We're pulling back the curtain. This is AI Deconstructed.
In our last episode, we met the Perceptron, our very first model of an artificial neuron. We saw it as a simple, yet surprisingly powerful decision-making unit. It takes in a set of inputs, each with an associated weight representing its importance, sums them up, and if that sum crosses a certain threshold, it fires. We established that at its core, the perceptron is a linear classifier. Its one and only trick is to learn how to draw a single straight line, or a flat plane in higher dimensions, to separate data into two distinct categories. Now imagine you're designing a very basic security system for a room with two motion sensors, one at the door and one at the window. You want an alarm to sound if someone enters through the door, or if someone comes through the window, but not if both sensors are triggered simultaneously, which might indicate a system malfunction or a friendly cat tripping both. And of course, you don't want the alarm to go off if nothing happens. This logic is called exclusive OR or XOR for short. One or the other, but not both. It seems like the simplest, most trivial piece of logic imaginable. And yet, this exact problem, this simple puzzle, became a monumental roadblock for the entire field of artificial intelligence. It was a challenge that our simple perceptron, the foundational building block of neural networks, was fundamentally, mathematically, incapable of solving. This failure was so profound that it helped trigger a decade of lost progress and funding, a period we now call the first AI winter. Today, we go under the hood to understand this critical moment in AI history. We will explore precisely why the perceptron fails at the XOR problem. By visualizing the concept of linear separability, we will uncover the story of the controversial book that highlighted this failure and lit the fuse for a crisis of confidence in AI. Then we will introduce the elegant architectural solution that saved the day, the multi-layer perceptron. We will build a deep intuitive understanding of how adding hidden layers of neurons allows a network to finally solve nonlinear problems. And finally, we'll touch upon the profound theoretical power this new architecture unlocked, paving the way for the AI revolution we see today. To understand the perceptron's great failure, we first need to build a solid intuition for what it can do. Its specialty is solving problems that are linearly separable. Imagine you have a garden, and you've planted two types of flowers, let's say red roses and yellow sunflowers. If all the roses are on one side of the garden and all the sunflowers are on the other, you can easily separate them by building a single straight fence right down the middle. In this case, your flower arrangement is linearly separable. The perceptron is your fence builder. If a straight fence can do the job, the perceptron can learn where to build it. Let's apply this to simple logic. Consider the AND gate. It only outputs a 1, or true, if both of its inputs are 1. Let's map this out. If input 1 is 0 and input 2 is 0, the output is 0. If input 1 is 0 and input 2 is 1, the output is still 0. If input 1 is 1 and input 2 is 0, the output is again 0. Only when input 1 is 1 and input 2 is 1, does the output become 1. If you picture these 4 points on a two-dimensional graph, with the point 1, 1 in the top right corner, you can easily see that a single straight line can be drawn to cleanly separate that lone true case from the other 3 false cases. The AND problem is linearly separable. A perceptron can solve it with ease. The same is true for the OR gate. The OR gate outputs true if at least one of its inputs is true. So 0, 0 gives 0, but 0, 1, 0, and 1, 1 all give an output of 1. Again, picture this on a graph. The point 0, 0 is at the bottom left corner. The other 3 points are all clustered away from it. You can easily draw a single straight line to fence off the single false case from the 3 true cases. The OR problem is also linearly separable. A perceptron has no trouble with it. Now we arrive at the villain of our story, the XOR gate. As we said, exclusive OR is true if one input is true but not both. Let's build its map. Input 0, 0 gives an output of 0. Input 0, 1 gives an output of 1. Input 1, 0 gives an output of 1. But input 1, 1 gives an output of 0. Now, visualize these 4 points on your graph. The 0 outputs are at the bottom left corner, at coordinate 0, 0, and the top right corner, at coordinate 1, 1. The 1 outputs are at the top left corner, 0, 1, and the bottom right corner, 0. They are diagonally opposed to each other. Now try to build your fence. Try to draw a single straight line that separates the 1s from the 0s. You can't. No matter where you draw that line, you will always have at least 1 point on the wrong side. You might group 3 points correctly, but the 4th will be an error. You might slice between 2, but you'll leave the other 2 mixed together. It is mathematically impossible. This is the definition of a non-linearly separable problem. And because the perceptron's only tool is that single straight line, it is fundamentally incapable of solving the XOR problem. If you try to train a perceptron on this data, it will thrash about, adjusting its weights endlessly, never converging on a solution. Its final accuracy will be about 50%, which is no better than flipping a coin to guess the answer. This seemingly trivial logic puzzle revealed a fatal flaw in the foundation of early neural networks. This isn't just a failure of visualization. We can prove it with the perceptron's own mathematics. Remember from last episode, the perceptron's rule for firing is when the weighted sum of inputs plus a bias is greater than some threshold. Let's set the threshold to 0, as is common. The neuron fires, outputting a 1 if 1 times zone plus WTWO times x2 plus b is greater than 0. It doesn't fire, outputting a 0 if 1 times zone plus WTWO times x2 plus b is less than or equal to 0. Let's plug in the 4 XOR points and see what happens. First, the input 0, 0 must output 0. We plug in zone equals 0 and x2 equals 0. This gives 1 times 0 plus WTWO times 0 plus b is less than or equal to 0. This simplifies to b is less than or equal to 0. Our bias must be negative or 0. Let's call this requirement 1. Second, the input 0, 1 must output 1. We plug in zone equals 0 and x2 equals 1. This gives 1 times 0 plus WTWO times 1 plus b is greater than 0. This simplifies to WTWO plus b is greater than 0. Let's call this requirement 2. Third, the input 0 must output 1. We plug in zone equals 1 and x2 equals 0. This gives 1 times 1 plus WTWO times 0 plus b is greater than 0. This simplifies to 1 plus b is greater than 0. This is requirement 3. Fourth, the input 1, 1 must output 0. We plug in zone equals 1 and x2 equals 1. This gives 1 times 1 plus WTWO times 1 plus b is less than or equal to 0. This simplifies to 1 plus WTWO plus b is less than or equal to 0. This is requirement 4. Now we have a system of 4 simple inequalities. Can any set of numbers for 1, WTWO, and b satisfy all 4 at the same time? Let's find out. From requirement 2, we know WTWO is greater than negative b. From requirement 3, we know 1 is greater than negative b. Let's add these 2 inequalities together. If WTWO is greater than negative b and 1 is greater than negative b, then their sum 1 plus WTWO, must be greater than negative B plus negative B. So, 1 plus WTWO is greater than negative 2B. Let's rearrange that. Let's add B to both sides. 1 plus WTWO plus B is greater than negative 2B plus B. This simplifies to 1 plus WTWO plus B is greater than negative B. Now let's look at requirement 1. We know B is less than or equal to 0. This means that negative B must be 0 or a positive number. So our combined inequality 1 plus WTWO plus B is greater than negative B is telling us that the term 1 plus WTWO plus B must be greater than some positive number, or 0. In other words, 1 plus WTWO plus B must be positive. But wait, look at requirement 4. It demands that 1 plus WTWO plus B is less than or equal to 0. It demands that this exact same term must be negative or 0. This is a complete, unbreakable logical contradiction. It is impossible for a number to be both greater than a positive value and less than or equal to 0 at the same time. The math falls apart. We have just proven formally that no perceptron can exist that can solve the XOR problem. The failure of the perceptron to solve the XOR problem wasn't just an academic curiosity. It became a central exhibit in a case against the entire field of connectionism, the branch of AI focused on neural networks. In the 1960s, the atmosphere surrounding AI research was one of boundless optimism. Pioneers of the field made bold predictions, and government agencies, particularly the Defense Advanced Research Projects Agency, or DARPA, were investing heavily, hoping for breakthroughs in machine translation, image recognition, and intelligent systems. Then, in 1969, two brilliant and highly respected AI researchers from MIT, Marvin Minsky and Seymour Papert, published a book titled, simply, Perceptrons. This book was not a casual critique. It was a rigorous, formal mathematical takedown of the single-layer perceptron model. They proved with mathematical certainty that these simple networks were fundamentally limited. They couldn't compute certain essential properties of their inputs. The most famous example they used was the XOR problem. But their analysis went deeper, showing that perceptrons also couldn't reliably determine if a shape in an image was a single connected object or multiple disconnected pieces, nor could they solve the parity problem, telling whether the number of active inputs was odd or even. Their argument was powerful and, on its own terms, correct. A single-layer perceptron simply lacked the computational capacity for these kinds of problems. However, the book was and remains deeply controversial. Critics pointed out that Minsky and Papert focused their analysis on a simplified, almost strawman version of the perceptron. Researchers like Frank Rosenblatt, the original inventor of the perceptron, were already exploring more complex architectures with multiple layers or feedback loops, which were not subject to the same limitations. The book, in a sense, proved the limits of a model that the field was already beginning to move beyond. In fact, Minsky and Papert even discussed the idea of multi-layer networks in their book. They acknowledged that stacking layers might overcome these limitations. But they then posed the truly devastating follow-up question. How would you train it? As we saw in episode 11, the perceptron learning rule is simple. The neuron makes a mistake. You know which neuron made the mistake. There's only one. You know which weights to nudge. But in a multi-layer network, if the final neuron is wrong, how do you know which neuron in the middle layer was responsible? How do you assign the credit or the blame for the final error? This credit assignment problem seemed unsolvable. With no known algorithm to train them, Minsky and Papert were deeply pessimistic about the future of multi-layer networks, dismissing them as computationally intractable. But the book's impact cannot be understood in a vacuum. It landed at the perfect moment to catalyze a growing sense of disillusionment. The entire AI field was running into a wall known as combinatorial explosion, where problems that were solvable in toy domains became computationally intractable in the real world. The grand promises of human-like intelligence weren't materializing. At the same time, the political winds were shifting. In the United States, the Mansfield Amendment forced DARPA to pivot from funding pure blue-sky research to mission-oriented projects with clear, short-term military applications. In the United Kingdom, the highly critical Lighthill report reached similar conclusions, leading to massive cuts in AI funding. Minsky and Pappert's book didn't create this environment, but it gave it a voice and a powerful mathematical justification. For policymakers and funding agencies losing patience with AI's slow progress, Perceptrons provided the perfect narrative. Neural networks have been mathematically proven to be a dead end. The effect was chilling. Funding for connectionist research all but vanished. The brightest minds in the field shifted their focus to other approaches, like symbolic AI, which we discussed in Episode 6. For more than a decade, research into neural networks languished. This period of stagnation became known as the first AI winter. The deep freeze of the AI winter eventually began to thaw, not because Minsky and Pappert's proofs were wrong, but because a new idea demonstrated they were incomplete. The limitation they identified was real, but it wasn't a fundamental barrier for neural networks as a whole. It was merely a limitation of a single-layer architecture. The solution, elegant in its simplicity, was to ask, what happens if we don't just use one perceptron, but stack them together in layers? This idea gave birth to the Multi-Layer Perceptron, or MLP, the architecture that would resurrect the field. Let's dissect the anatomy of an MLP. It's a more sophisticated structure, but it's built from the same simple neurons we already understand. First, we have the input layer. This isn't really a computational layer. Think of it as the reception desk for our network. It has one neuron for each feature in our data. For the XOR problem, which has two inputs, zone and x2, our input layer would have two neurons. Their only job is to receive the input values and pass them along to the first real processing layer. Next, and this is the revolutionary addition, we have one or more hidden layers. These are layers of neurons tucked between the input and the output. They are called hidden because their operations are entirely internal to the network. We don't feed them data directly, and we don't see their final output. This is where the heavy lifting happens, where the raw data is transformed and reinterpreted. The presence of at least one hidden layer is what distinguishes an MLP from a simple perceptron. Finally, we have the output layer. This last layer of neurons receives the processed information from the final hidden layer and produces the network's ultimate prediction. For a binary classification problem like XOR, this might be a single neuron that outputs a value close to 0 or 1. Within this structure, information flows in a very specific way. This is a feed-forward network. Data enters at the input layer, moves forward through the hidden layer or layers, and exits at the output layer. There are no loops, no cycles, no going backward. The signal propagates in one direction only. This is a key distinction from other architectures we'll meet later in this course, like recurrent neural networks, which are designed specifically to handle cycles and memory. Furthermore, in a standard MLP, the layers are fully connected, which is sometimes called dense. This means that every single neuron in one layer is connected to every single neuron in the very next layer. So, zone from the input layer connects to every neuron in the hidden layer. X2 also connects to every neuron in the hidden layer. Then, every neuron in the hidden layer connects to every neuron in the output layer. Each one of these countless connections has its own unique weight, a parameter that the network will learn during training. This dense web of connections is what allows the network to learn rich, complex relationships between its layers. So, we have our new architecture, a stack of fully connected layers with information flowing forward. But this raises a critical question. If each neuron is just a linear classifier, a simple line drawer, and we just stack them together, aren't we just combining a bunch of straight lines to get another straight line? This is a common and very insightful question. If the entire network were purely linear, the answer would be yes. Stacking linear operations just results in another linear operation, and the whole multi-layer network would collapse back into a single, limited perceptron, still incapable of solving XOR. The magic ingredient, the secret sauce that unlocks nonlinearity, is the activation function we apply within the hidden neurons. In our original perceptron, this was a simple harsh step function. If the sum is over the threshold, fire 1, otherwise fire 0. For MLPs, we use slightly different smoother functions, a topic so important we're dedicating all of episode 14 to it. For now, the key takeaway is that after a hidden neuron sums up its weighted inputs, it passes that sum through a nonlinear filter before sending its signal forward. This nonlinear step is what breaks the chain of linearity and gives the network its power. But before we get to the math, let's build an intuition for what's happening. Let's use an analogy. Think of the single perceptron as a single overworked judge trying to decide a complex case with only one simple rule, a straight-line division. For the XOR problem, this judge failed. A multi-layer perceptron, on the other hand, is like a well-structured legal team. The hidden layer is a panel of junior analysts. Each analyst is still relatively simple. They can only draw one straight line, just like our original perceptron, but they are each given a different part of the problem to analyze. For the XOR problem, let's build an MLP with two neurons in its hidden layer. The senior partner, the output layer, gives the first analyst, hidden neuron 1, a specific task. Draw a line that separates the case where both inputs are 0 from all the other cases. This is the OR function, which we know is linearly separable. Analyst 1 draws their line and files a report, yes or no. The senior partner gives the second analyst, hidden neuron 2, a different task. Draw a line that separates the case where both inputs are 1 from all the other cases. This is equivalent to a NAND function, or NOTAND, which is also linearly separable. Analyst 2 draws their line and files their own report. Now here is the crucial step. The senior partner, our output neuron, never looks at the original messy data. They are far too busy for that. They only look at the two simple reports submitted by their junior analysts. Their job is now incredibly easy. They apply a simple rule. If Analyst 1 reported yes and Analyst 2 reported yes, then the final verdict is true. Otherwise, a verdict of false. This final decision is itself a simple linear separation, an AND gate, but it's being performed on the transform data, the high-level reports from the hidden layer, not the raw inputs. Let's trace this and prove that it works. Our network has two inputs, zone and x2. It has two hidden neurons, hone and HTWO. It has one output neuron. Hone has learned to be an OR gate. HTWO has learned to be a NAND gate. The output neuron has learned to be an AND gate. Case 1. Input is 0, 0. The correct XOR output is 0. Input 0, 0 goes to the hidden layer. Hone, our OR neuron, sees 0, 0. It outputs 0. HTWO, our NAND neuron, sees 0, 0. It outputs 1. the hidden layer has transformed the input 0, 0 into a new representation 0, 1. This new representation 0, 1 is fed to the output layer, the output neuron, which is an AND gate, sees 0, 1. It outputs 0. The final output is 0. This is correct. Case 2. Input is 0, 1. The correct XOR output is 1. Input 0, 1 goes to the hidden layer. Hone, the OR neuron, sees 0, 1. It outputs 1. HTWO, the NAND neuron, sees 0, 1. It outputs 1. The hidden layer has transformed the input 0, 1 into a new representation 1, 1. This 1, 1 is fed to the output layer. The output neuron, the AND gate, sees 1, 1. It outputs 1. The final output is 1. This is correct. Case 3. Input is ONA 0. The correct XOR output is 1. Input ONA 0 goes to the hidden layer. Hone, the OR neuron, sees ONA 0. It outputs 1. HTWO, the NAND neuron, sees ONA 0. It outputs 1. The hidden layer has transformed the input ONA 0 into a new representation 1, 1. This 1, 1 is fed to the output layer. The output neuron, the AND gate, sees 1, 1. It outputs 1. The final output is 1. This is correct. Case 4. Input is 1, 1. The correct XOR output is 0. Input 1, 1 goes to the hidden layer. Hone, the OR neuron, sees 1, 1. It outputs 1. HTWO, the NAND neuron, sees 1, 1. It outputs 0. The hidden layer has transformed the input 1, 1 into a new representation, ONA 0. This ONA 0 is fed to the output layer. The output neuron, the AND gate, sees ONA 0. It outputs 0. The final output is 0. This is correct. The network works perfectly. But how? The hidden layer isn't trying to solve the whole problem at once. It's learning to act as a team of feature extractors. Each neuron in the hidden layer learns to draw a different straight line, separating the input space in a way that is useful. The output layer then takes these new high-level features, the report from the OR neuron and the report from the NAND neuron, and learns a simple linear combination of them. The problem has been transformed. Look at the problem the output neuron had to solve. It received these inputs, 0, 1, 1, 1, 1, 1, and ONA 0. It had to output 0, 1, 1, and 0. Is this problem linearly separable? Let's plot it in the new hidden space. We have class 0 inches points at 0, 1 and ONA 0. We have class 1 inch points at 1, 1. It gets this input twice, but that's fine. Can you draw a line to separate 0, 1 and ONA 0 from 1, 1? Of course, the AND function we used is just such a line. The network solves XOR not by drawing a single curved line in the original two-dimensional space, but by projecting the 4 input points into a new, higher dimensional space defined by the activations of the hidden layer. In this new space, the points that were once tangled together become cleanly, linearly separable. The hidden layer learns to warp and remap the data's geometry, entangling the knot of XOR so that a simple linear decision can finish the job. This ability to learn new representations of data is the fundamental power of deep learning. The multi-layer perceptron's ability to solve the XOR problem was more than just a clever trick. It was a proof of concept that hinted at a much deeper power. It led researchers to ask a profound question. If stacking layers can solve this one nonlinear problem, are there any limits to what it can solve? What is the true expressive capacity of this architecture? The answer came in the form of one of the most important theoretical pillars of deep learning, the universal approximation theorem. The theorem is a stunning statement. First formally proven in 1989 by George Cybenko, it states that a feed-forward network with just a single hidden layer, containing a finite number of neurons and a nonlinear activation function, can, in principle, approximate any continuous function to any desired degree of accuracy. Let's unpack that with an analogy. Think of the neurons in that hidden layer as different types of Lego bricks. A single brick is very simple. It has a fixed shape and size. But if you have a large enough collection of bricks of various types, you can build a representation of anything. You can build a simple house. You can build a complex curving sculpture. You can build a detailed model of a spaceship. The universal approximation theorem says that, given enough neurons in that single hidden layer, enough Lego bricks, you can construct a mathematical function that can mimic the shape of any other continuous function you can imagine, no matter how complex its twists and turns. The more neurons you add, the more bricks you have to work with, and the finer the detail of your approximation can be. This is an incredibly powerful idea. It provides the mathematical justification for why we believe neural networks can work on such a vast range of problems. It assures us that, for almost any mapping from inputs to outputs we want to learn, there is a neural network out there that has the raw architectural capacity to represent it, from the function that maps pixels of a cat to the word cat, to the function that maps audio waves to transcribe text. This theorem tells us a solution is possible. However, the universal approximation theorem is also one of the most misunderstood and overhyped concepts in AI. So, as part of our mission to build genuine literacy, we must correct some common misconceptions. First is the misconception that the theorem means a neural network can solve any problem. This is false. The theorem is an existence proof, not a practical blueprint. It guarantees that a network with the correct weights and biases exists, but it gives us absolutely no information on how to find those parameters. The process of finding them, which we call training, can be incredibly difficult or even impossible. It's like knowing that a perfect Lego sculpture of the Mona Lisa is possible, but having no instructions on how to build it from a giant pile of bricks. The search for those correct weights is the entire challenge of machine learning, a challenge we will begin to solve in our next episode. The second misconception is that the theorem applies to everything. The formal theorem has specific conditions. It applies to approximating continuous functions, functions that don't have sudden infinite jumps or breaks. And it technically applies over a compact, which just means a bounded set of inputs. This means a network trained to approximate a function for inputs between 0 and 10 has no guarantee of how it will behave when you give it an input of 100. It's great at interpolation. That is, making predictions within the range of data it's seen, but it's often terrible at extrapolation, or making predictions outside that range. A network trained on house prices in Ohio has no meaningful concept of what a house in Tokyo should cost. Finally, there's the idea that more neurons are always better. While the theorem relies on having enough neurons, it doesn't tell us how many is enough. In practice, building a network that is too wide, with too many neurons in its hidden layer, can be computationally expensive and, more importantly, can lead to a problem called overfitting. This is where the network essentially memorizes the training data instead of learning the underlying general pattern. It's like a student who crams for a test by memorizing the answers to the study guide, but doesn't actually understand the material. Such a network will perform perfectly on the data it has seen, but fail miserably on new, unseen examples. So, the universal approximation theorem is our guarantee of potential. It tells us the tool is powerful enough for the job, but it doesn't do the job for us. The art and science of deep learning lies in designing architectures and training procedures that can actually find that needle in the haystack, the one specific configuration of weights that successfully approximates the function we care about. Given its history as the model that thawed the first AI winter, it's natural to ask where the multi-layer perceptron fits into the modern AI landscape. which is so often dominated by headlines about massive complex architectures like transformers. Is the MLP just a historical artifact, a stepping stone we've since left behind? The answer is a definitive no. The MLP is not only still relevant, it is quietly one of the most ubiquitous and essential components in modern AI. First, for a huge class of problems, the vanilla MLP remains a powerful go-to tool, specifically for tasks involving tabular data, the kind of data you'd find in a spreadsheet or a database. The MLP is often a first-choice model. Think about a bank trying to predict whether a customer will default on a loan based on their income, credit score, age, and other factors, or an insurance company trying to predict the price of a policy, or a doctor trying to make a diagnosis based on a patient's lab results. These are all classification or regression problems on structured tabular data, and MLPs excel at them, learning the complex nonlinear relationships between the features. But the most significant role of the MLP today is not as a standalone model, but as a critical building block inside nearly every other advanced architecture. There's a powerful saying among some machine learning engineers: everything is MLPs. What they mean is that even the most sophisticated models rely on MLPs to do essential work. Consider the task of transfer learning, which we'll explore in our computer vision unit. A research lab might spend millions of dollars training a giant vision model on 1 billion images. That model becomes an expert feature extractor. It learns to see edges, textures, shapes, and objects. Now, say you want to use that model for a very specific task, like identifying different types of trees in a forest. You don't need to retrain the whole model. You take the pre-trained model, chop off its final output layer, and add a new small network on top to make your specific predictions. That small network you add, the classification head or regression head, is almost always a simple multi-layer perceptron. The giant specialized architecture does the heavy lifting of perception, and the humble MLP takes those sophisticated features and makes the final, decisive classification. This pattern appears everywhere. Even inside the famous transformer architecture, the engine behind models like GPT-4 and all modern LLMs, there is a crucial component called the feed-forward network. After the attention mechanism weighs and mixes the information from the input text, it's a simple MLP that processes that information before passing it to the next layer. When we get to episode 20, we'll open up the transformer and find this unassuming MLP block sitting right at the heart of it. The MLP is not just an add-on. It's a core part of the engine that powers the most advanced AI systems in the world today. It is the foundational component that provides the nonlinear processing power that all deep learning models depend on. So, in this episode, we have traced a dramatic arc in the history of artificial intelligence. We began with the simple perceptron, a model that could only draw straight lines, and we saw its world-shattering failure when confronted with the simple, nonlinear puzzle of the XOR problem. We witnessed how this failure, amplified by the rigorous critique in Minsky and Papert's book Perceptrons, provided justification for the funding cuts that ushered in the first AI winter, a period of stagnation and disillusionment. But from that winter, a more powerful idea emerged: the multi-layer perceptron. By adding one or more hidden layers, the network gained the ability to do something extraordinary. It learned not just to classify data, but to first transform it, to create new higher-level representations in which complex problems become simple. This is the mechanism that allows neural networks to create the complex, nonlinear decision boundaries needed to solve real-world problems. We learned that the theoretical power of this architecture is immense, as captured by the universal approximation theorem, which guarantees that an MLP has the capacity to approximate almost any function. But we also armed ourselves with a healthy skepticism, understanding the practical caveats and common misconceptions that surround this powerful theorem. The leap from the single-layer perceptron to the multi-layer perceptron was not just an incremental improvement. It was a fundamental paradigm shift. It was the moment that artificial intelligence learned to move beyond the rigid world of simple lines and started learning to model the complex, high-dimensional, and nonlinear landscapes that represent reality. This ability to learn representations, to bend and warp the very geometry of a problem, is the bedrock upon which all of modern deep learning is built. We've now constructed an incredibly powerful machine. We have an architecture that, in theory, can learn almost anything, but a crucial question remains unanswered. How does it actually learn? How does this vast network of millions of connections and weights go from a random, useless configuration to a finely tuned, expert problem solver? We hand-waved our XOR solution by saying one neuron learns OR and another learns NAND. But how? That is the credit assignment problem that Minsky and Papert warned us about. To answer that, we need to open up the hood and look at the engine of learning itself. In our next episode, we will deconstruct the two most important algorithms in all of deep learning: gradient descent and backpropagation.
You've been listening to AI Deconstructed. Join us next time as we unpack another layer of the technology shaping our future. Until then, stay curious. Subscribe for more.